Welcome to this scientific lecture on one of the most fascinating phenomena in nanotechnology, surfaces that can instantly switch between loving water and hating water, controlled by tiny electrical or chemical signals. Imagine a surface that can change from being completely water repellent, like a lotus leaf, to completely water-loving, like a clean glass window, in a fraction of a second. This isn't science fiction. This is the reality of nanostructured switchable surfaces. You might ask, why does this matter? Well, these surfaces have applications in microfluidics, self-cleaning materials, fog harvesting, oil-water separation, and even biomedical devices. The ability to control water at the nanoscale opens up extraordinary possibilities. Let's start with the fundamentals. How do we measure how much a surface loves or hates water? The contact angle theta is the angle between the water droplet surface and the solid surface. This single number tells us everything about wettability. If theta is less than 90 degrees, the surface is hydrophilic, meaning water-loving. The droplet spreads out. If theta is greater than 90 degrees, the surface is hydrophobic, meaning water-repelling. The droplet beads up. But here's where it gets exciting. If theta is greater than 150 degrees, we call it superhydrophobic. Water droplets become nearly spherical and roll off effortlessly. Conversely, if theta is less than 10 degrees, the surface is superhydrophilic. Water spreads into an extremely thin film almost instantly. For a perfectly smooth surface, the contact angle is determined by Young's equation, which relates the surface tensions at the three interfaces. Cosine of theta y equals gamma SV minus gamma SL, all divided by gamma LV. Here, theta y is Young's contact angle. Gamma SV is the solid vapor interfacial tension, gamma SL is the solid liquid tension, and gamma LV is the liquid vapor tension, which for water is about 72 millinewtons per meter. Here's a critical insight. Young's equation shows that smooth surfaces alone, no matter what chemistry you use, cannot achieve superhydrophobicity. You need roughness. This is where nanostructure comes in. Roughness amplifies the natural wetting properties of a material. Imagine a surface covered with nanoscale pillars or ridges, like a tiny forest. When a water droplet sits on this surface, it doesn't penetrate all the way down. Instead, air pockets get trapped beneath the droplet. This leads us to two critically important wetting states, the Cassie state and the Wenzel state. In the Cassie state, named after ABD Cassie, the droplet sits on top of the roughness features with air trapped underneath. This is the superhydrophobic state. In the Wenzel state, named after Robert Wenzel, the liquid completely penetrates and fills all the valleys between the roughness features. This typically gives high adhesion. Let's write down the equation for the Cassie state. This is fundamental. Cosine theta C equals F1 times cosine theta Y plus F2 times cosine of 180 degrees. Theta C is the Cassie contact angle. Since cosine of 180 degrees is -1, this simplifies to cosine theta C equals F1 times cosine theta Y minus F2. Here, F1 is the fraction of the droplet base in contact with solid, and F2 is the fraction in contact with air. Obviously, F1 plus F2 equals 1. The key insight is that increasing the air fraction F2 makes the contact angle larger, approaching 180 degrees for a perfectly non-wetting composite interface. Let's do a numerical example. Consider silicon nanopillars, where the intrinsic Young angle for silicon dioxide is about 70 degrees. Say theta y is 70 degrees, F1 is 0.1, meaning only 10% solid contact, and F2 is 0.9. Then cosine theta C equals 0.1 times cosine 70 degrees minus 0.9. Cosine of 70 degrees is approximately 0.342. So we get 0.0342 minus 0.9, which equals -0.866. The arcosine of -0.866 gives us approximately 150 degrees. This is superhydrophobic. Now let's examine the Wenzel state, where liquid fills all the roughness. Cosine theta W equals R times cosine theta Y. Here R is the roughness factor. The roughness factor R is the ratio of the actual surface area, including all the hills and valleys, to the projected flat area. For rough surfaces, R is always greater than 1. The Wenzel equation tells us that roughness amplifies the intrinsic wetting property. If the surface is hydrophilic, roughness makes it more hydrophilic. If hydrophobic, roughness makes it more hydrophobic. For example, if R equals 3 and theta y is 70 degrees, then cosine theta w equals 3 times 0.342, which is 1.026. But wait, cosine cannot exceed 1. This means the denominator forces complete wetting. The contact angle becomes 0 degrees, the liquid spreads completely. Here's the million-dollar question. What causes a droplet to transition from the Cassie state to the Wenzel state, or vice versa? The answer involves energy barriers and applied forces. The Cassie state is often metastable, meaning it's stable but not the absolute lowest energy state. Let's talk about capillary pressure, which governs these transitions. This is where the nanoscale becomes crucial. The capillary pressure is given by delta P equals 2 gamma L V cosine theta divided by R. Here R is the radius of curvature of the meniscus. For nanoscale features, R might be just 10 nanometers. This makes the pressure enormous. Let's estimate. For water, gamma LV is 72 millinewtons per meter. If R is 10 nanometers and theta is 90 degrees, so cosine theta is 0, the pressure is still determined by slight deviations. Taking a small advancing angle of, say, 110 degrees, cosine is about negative 0.34. We get delta P approximately 2 times 0.07, 2 times 0.34, divided by 10 times 10 to the negative 9, which is about 5 megapascals. That's 50 atmospheres of pressure. This huge pressure can either stabilize the Cassie state by preventing liquid penetration, or force a transition to Wenzel if the pressure exceeds the surface's ability to resist. There's a critical pressure above which the Cassie state collapses into the Wenzel state. The critical pressure is given by P critical equals negative 2 gamma LV cosine theta y divided by D, where D is the spacing between pillars. If D is 50 nanometers and theta y is 110 degrees, then cosine theta y is about negative 0.34. P critical equals 2 times 0.07, 2 times 0.34 divided by 50 times 10 to the negative 9, which gives about 1 megapascal. This is the pressure needed to force the transition. Now let's explore electro-wetting, one of the most elegant ways to switch wetting states electrically. In electro-wetting, we apply a voltage between a conductive liquid droplet and an electrode beneath a thin dielectric layer. The electric field modifies the apparent surface energy. The fundamental equation governing electro-wetting is the Lippmann-Young equation. Cosine theta V equals cosine theta Y plus epsilon 0 epsilon R times V squared, divided by 2D gamma LV. Here, V is the applied voltage, D is the thickness of the dielectric layer, epsilon 0 is the permittivity of free space, and epsilon R is the relative permittivity of the dielectric. The key insight is that applying voltage always reduces the contact angle, making the surface more hydrophilic. The effect goes as V squared, so polarity doesn't matter. Let's calculate the voltage needed to switch from 150 degrees to 10 degrees on a nanorow surface. Assume theta y is 110 degrees, dielectric thickness D is 100 nanometers, and epsilon R is 4 for a typical polymer dielectric. We want to go from Cassie at 150 degrees to Wenzel-like at 10 degrees, so cosine 10 degrees minus cosine 110 degrees equals the electro-wetting term. Cosine of 10 degrees is 0.985, and cosine of 110 degrees is negative 0.342. The difference is 1.327. Solving for V squared. V squared equals 1.327 times 2 times 100 times 10 to the negative 9 times 0.072 divided by epsilon 0 times 4. Epsilon 0 is 8.85 times 10 to the negative 12. Calculating this out gives V approximately 60 volts. This is a reasonable voltage for lab devices. When you combine electro-wetting with nanoroughness, something magical happens. You can electrically trigger the Cassie to Wenzel transition. At 0 volts, the surface is in the Cassie state with trapped air, exhibiting superhydrophobicity with contact angle above 150 degrees. When you apply high voltage, the reduced contact angle causes the liquid to penetrate the nanostructure, transitioning to the Wenzel state. Now the surface becomes superhydrophilic with contact angle near zero. You might ask, is this reversible? Can we go back from Wenzel to Cassie by removing the voltage? The answer is not easily. The Wenzel state is often a deeper energy minimum. To reverse it, you typically need to dry the surface or apply mechanical vibration to nucleate air pockets. However, with very careful nanostructure design, such as re-entrant geometries or hierarchical structures, researchers have achieved reversible switching by preventing full Wenzel penetration. Now let's discuss how scientists experimentally map these wetting transitions. This is real lab work. Method 1 is contact angle goniometry. You place a droplet on the surface and use a high-speed camera to measure the contact angle as a function of applied voltage or pressure. Method 2 is confocal laser scanning microscopy. By adding fluorescent dye to the water, you can directly image whether the liquid penetrates the nanostructure or sits on top with trapped air. Method 3 is atomic force microscopy in liquid. You can probe the mechanical response of the interface and detect the presence of air pockets by measuring the force curves. Method 4 is electrical impedance spectroscopy. The Cassie and Wenzel states have different electrical impedances because air has very different dielectric properties than water. Let me describe a typical experiment. You fabricate silicon nanopillars with controlled spacing and height, then coat them with a hydrophobic layer. Step 1. At 0 volts, you measure the contact angle. It should be around 155 degrees in the Cassie state with high air fraction. Step 2. You increase the voltage in steps of 10 volts, waiting for equilibrium after each step, and measure the contact angle. Step 3. You observe a sharp transition. The contact angle suddenly drops from 150 degrees to below 20 degrees. This is the Cassie to Wenzel transition. Step 4. You use confocal microscopy with fluorescent water to directly confirm that the air pockets have collapsed and water now fills the valleys. Step 5. You repeat this for different pillar spacings and create a phase diagram showing the critical voltage as a function of geometry. Besides electrical control, you can also trigger wetting transitions chemically using pH changes or surfactants. Some polymers change their hydrophobicity with pH. For example, polyacrylic acid becomes charged and hydrophilic at high pH, but neutral and hydrophobic at low pH. Surfactants reduce the surface tension gamma LV. From our equations, reducing gamma LV reduces the capillary pressure, making it easier for liquid to penetrate the roughness and trigger the Cassie to Wenzel transition. For example, if gamma LV drops from 72 millinewtons per meter to 30 millinewtons per meter with surfactant, the critical pressure drops by more than a factor of 2, facilitating the transition. Let's discuss the profound implications and applications of these switchable surfaces. Application 1 is smart microfluidics. You can electrically control droplet motion, mixing, and splitting by locally switching surface wettability. This enables lab-on-a-chip devices with no moving parts. Application 2 is anti-fouling coatings. By periodically switching between superhydrophobic and superhydrophilic states, you can release trapped contaminants and self-clean the surface. Application 3 is water harvesting from fog. In the Cassie state, tiny fog droplets coalesce and roll off. By switching to Wenzel, you can pin larger droplets for collection. Application 4 is tunable optical properties. The Cassie state with trapped air has different refractive index than the Wenzel state. This enables electrically switchable optical coatings. Application 5 is drag reduction in microchannels. The Cassie state provides slip boundary conditions, reducing hydrodynamic drag by up to 40% compared to the Wenzel state. Despite decades of research, there are still fascinating open questions in this field. Question 1. Can we design nanostructures that allow fully reversible Cassie to Wenzel transitions without external drying or mechanical agitation? Question 2. What happens at the molecular scale at the three-phase contact line when the transition occurs? Can we simulate this with molecular dynamics? Question 3. How do we minimize contact line pinning and hysteresis on nanorow surfaces to achieve ultra-low friction droplet rolling? Question 4. Can we scale these precisely engineered nanostructures to large areas at low cost for industrial applications? Let's touch on an advanced topic, hierarchical structures, which combine micro and nano roughness. Nature uses hierarchical roughness. The lotus leaf has microscale bumps covered with nanoscale wax crystals. This dual-scale roughness provides exceptional superhydrophobicity with contact angles exceeding 160 degrees. Hierarchical structures are more robust against the Cassie to Wenzel transition because the microscale features provide structural support, while the nanoscale features maintain the air pockets. For hierarchical structures, the Cassie equation becomes nested. Cosine theta h equals F1 micro times the quantity, F1 nano, cosine theta y minus F2 nano, all minus F2 micro. The micro and nano contributions multiply together. This hierarchical amplification allows contact angles approaching 180 degrees with extremely low contact angle hysteresis. Another advanced concept is re-entrant geometries, where the structure overhangs to create a mechanical trap for air. Re-entrant structures have overhangs shaped like mushroom caps or inverse trapezoids. Even if the intrinsic contact angle is less than 90 degrees, the geometry prevents liquid from penetrating downward. Re-entrant structures are key to omniphobic surfaces that repel not just water, but also oils and other low-surface tension liquids. Let's think about wetting transitions from an energy landscape perspective. This is intellectually beautiful. Imagine a plot of free energy versus some configuration coordinate. There are two minima, one for Cassie and one for Wenzel. The Wenzel state is typically lower in energy, but there's an energy barrier between them. An external stimulus, whether electrical, mechanical, or chemical, provides the energy to overcome the barrier and transition from Cassie to Wenzel. The height of this barrier depends on the nanostructure geometry, the pillar spacing, the intrinsic contact angle, and the liquid surface tension. The energy barrier scales roughly as delta E proportional to gamma LV times L squared, where L is the characteristic length scale of the roughness features. For nanoscale features, L is on the order of 10 to 100 nanometers, so the barrier is small. This enables fast, low-energy transitions. In real applications, we care about dynamic contact angles, not just static equilibrium angles. The advancing angle is measured as a droplet expands and the contact line moves outward over fresh surface. The receding angle is measured as the droplet contracts and the contact line recedes. Contact angle hysteresis is the difference. Theta advancing minus theta receding. Low hysteresis is crucial for droplet mobility. The Cassie state typically has very low hysteresis, often less than 5 degrees, because the contact line can easily move over the air pockets. The Wenzel state has high hysteresis because the contact line gets pinned in the roughness valleys. This is why the Cassie state is desirable for self-cleaning surfaces. Droplets roll off easily, carrying away contaminants. Let's be honest about the limitations and challenges facing this technology. Challenge 1 is mechanical durability. Nanostructures are fragile. Abrasion, impact, or even touching can damage the delicate pillars and destroy the superhydrophobic properties. Challenge 2 is chemical stability. Many hydrophobic coatings degrade under UV light, oxidation, or chemical exposure, losing their low surface energy. Challenge 3 is fabrication cost. Techniques like electron beam lithography or focused ion beam milling are expensive and slow, limiting scalability. Challenge 4 is ice formation. At low temperatures, water can freeze inside the nanostructure, irreversibly transitioning to a Wenzel-like state with high adhesion. But researchers are actively addressing these challenges with innovative solutions. Solution 1. Use hierarchical structures. The microscale features protect the nanoscale features from mechanical damage. Solution 2. Develop self-healing hydrophobic coatings that can regenerate low surface energy after damage by migration of hydrophobic molecules from a reservoir. Solution 3. Employ scalable fabrication methods like nanoimprint lithography, colloidal self-assembly, or electrochemical etching to reduce costs. Solution 4. Incorporate anti-icing strategies such as slippery liquid-infused porous surfaces, or slips, where a lubricating oil fills the nanostructure instead of air. Let me conclude this lecture with some broader thoughts about what we've learned. We've seen how nanoscale geometry combined with surface chemistry gives us exquisite control over how liquids interact with surfaces. We've developed rigorous mathematical models, the Cassie, Baxter, and Wenzel equations, that quantitatively predict experimental behavior. We've demonstrated that tiny electrical voltages, or chemical changes can trigger dramatic reversible or irreversible transitions between wetting states. The applications span diverse fields, from biomedical microfluidics to energy-efficient water harvesting to self-cleaning windows. This research exemplifies biomimicry. By understanding how the lotus leaf and butterfly wings manipulate water at the nanoscale, we engineer superior human-made materials. The field remains vibrant, with open questions about reversibility, molecular scale mechanisms, scalability, and durability driving ongoing research. Ultimately, these nanoscale surfaces teach us a profound lesson. By controlling structure at the nanometer scale, we achieve transformative macroscale properties that impact everyday life. Thank you for joining me on this scientific journey through the fascinating world of switchable wetting at the nanoscale. The interplay of physics, chemistry, and engineering at these tiny dimensions opens up possibilities we are only beginning to explore.